Thanks. Well, thank you for having me today. I came back to Australia, as I was mentioning earlier, mainly for my family. I absolutely adored being in Canada, but I needed my family to understand what it was like to be Australian, not just Canadian. And when I looked at opportunities to come back, I wanted to stay in my preferred field, which is flotation. And when an opportunity presented itself with the Jameson Cell, I was just like, oh, this is just, you know, great things colliding. I'd worked with the Jameson Cell in the early 90s at Mount Isa, and for the first few years, I absolutely detested the technology. It was a pain in the ass. And then somebody came up with a new development. It was as simple as being able to feed a constant flow rate. Now, that doesn't sound technically very difficult, but it transformed the technology from being a dog to something that I'm proud to have my name associated with today. It simply transformed it. And I put Jameson Cells in Mount Isa in the early 2000s. They're operating successfully today. And without me, they put in Jameson Cells again in Mount Isa in 2015, which is one of the case studies I'll talk about today. So I love the Jameson Cell because, in my opinion, it makes the best bubbles in the world. And if you're dealing with flotation, it's all about the bubbles. So what am I going to look at today? I wasn't sure how many of you were familiar with the Jameson Cell, and I presented recently in Canada, and Peter Munro said, oh, that was terrible. You didn't show the video and you didn't show the basics of the Jameson Cell. So, Peter, I'm listening. I'll show that today. I'll go through the basic cell designs really quickly just to make sure you understand what I'm talking about. And then I'll look at why we think the Jameson Cell is best suited in the cleaner circuit, and we'll show you the design that we use in concentrators now, and just go through a couple of case studies. Both happen to be Glencore, but I could have provided other case studies had I needed to. So Professor Jameson was invited up to Mount Isa in the mid-80s, and he was tasked with looking at a way of actually improving sparges. That was the original project, because the sparges in those days were horrible perforated tubes with rubber socks, and they were just absolutely awful, and they deteriorated very rapidly. And as you know, bubble size is a fundamental of flotation. So as soon as the bubbles got big, the column performance dropped off. So he was tasked to improve that. And he looked at the columns and says, why the hell do you need such a huge volume to essentially bring together bubbles and particles? So he thought there must be a much better way of doing it. And so that's what he came up with. And essentially he developed the downcomer, which is the fundamental component of the Jameson Cell. It's where the bubbles are generated, and it's where the bubble-particle collision occurs. The flotation in a Jameson Cell is exceptionally fast. So the photo you see here is actually the lead zinc concentrator in Mount Isa, and you'll see it's got three 2.5 by 16 metre columns, and then right next to it, it has two 1.9 metre Jameson Cells. Now, each of those little Jameson Cells treats the same volumetric flow rate as the columns, and each can recover the same amount of concentrate. So it's a pretty simple photo to see that there is a huge benefit in designing and transforming concentrators in terms of the size of the footprint and the efficiency of the process. When I was looking through the seminars that you've had in the past, I looked at one that Joe Pease had given, and he talked about the innovation valley of death. So I thought I'd present that here and show how the Jameson Cell, in some areas, fell into that valley of death. So if you're not familiar, there's the 5 stages, and they represent the adoption curve given in black. And in this case, I've said it's a 30 years adoption curve, which is accepted in industry that that's about what it takes. You think, when was the first SAG mill invented? When did they become mainstream? You know, the Isa mill, when was it invented? When did it become mainstream? So if you look at the first 10 years in both coal and base metals, the technology, people looked at it and said, ah, that makes sense. Makes lots of sense. Yeah. And they adopted it. But what happened was it wasn't ready. So in coal, they said, oh, that's okay. We value this technology, so we're going to make it better. And it was the coal industry that solved the constant volumetric flow problem. So they arranged it such that a portion of the tailings could flow back to the feed pump box, and you could run a fixed speed pump and thus constant flow. As I say, it's not rocket science, but it makes a huge difference to the operation of Jameson Cell because it's fundamental. Unfortunately, the base metal industry just said it doesn't work and gave up on it. And as you can see, it's only been in the last 10 years that the technology has again taken off in base metals. So this is the video that Peter said I must show. Let's just get that volume working.
Here we're operating with water and froth alone. After a short contact period, the bubbling mixture flows downwards into the cell proper, where the bubbles disengage. Now we have coal in the feed of the downcomer. The intense turbulent mixing breaks the airstream into small bubbles, which then make violent contact with the particles.
Don't you love that? Violent contact with particles. And essentially that's what it is. It is violent contact. One of the fundamentals of the Jameson is that every bit of the feed, every bit of that slurry is pumped through a downcomer. The volumetric flow required for your process, you just add more and more downcomers, but every bit of the feed goes through a downcomer. So every bit of your feed slurry has an opportunity to see a bubble. That's not the case in other technologies. So how does it work? We pump the slurry down through the orifice. The orifice in the that we use right now is about 44 millimeters, so it's a decent size. The early models, it was only about 25, so you can imagine much more prone to blockage, etc. Operating about the same pressure you might operate a cyclone at, so it's not an extraordinarily high pressure. The jet, obviously you fill up the tank. As the tank fills, you form a hydraulic seal at the bottom of the downcomer, and at that point the slurry is sucked up the downcomer by the vacuum. You can control the air rate, so as opposed to other machines that draw their air in, we control it. So you must have a vacuum to control the level in your downcomer for your flotation to happen in your downcomer. So we control the airflow sucked in from atmosphere. So the jet plunges into that slurry, as you saw during the video. It shears the air into very fine bubbles and very intense mixing, and the bubbles and particles make violent contact. Because now you have the buoyancy acting and the slurry is flowing out the bottom of the downcomer, you end up with a very high void fraction, lots of air inside the downcomer, which is once again very favourable for flotation. And what that means is you get many more successful bubble particle collisions than you would in a regular cell. All of the flotation in the Jameson cell takes place in the downcomer. And I think it was Greg Harbert who, in his PhD, actually studied, well, do particles drop off and reattach in the tank? And the answer is no, it almost exclusively takes place in the downcomer. So therefore your residence time, because it's just in the downcomer, is a matter of seconds. So once you've collected, you've got essentially a plug flow going down your downcomer. The bubbles exit the downcomer and gently rise and are distributed across the tank and form a very, very stable froth layer. As mentioned, the fixed feed flow rate is the absolutely critical parameter. You can imagine if the flow rate varied, you're going to have varying level in the downcomer, you're going to have varying pressure, varying amount of air coming in, so it was a critical improvement to make sure that you had constant feed flow rate. And as mentioned, every particle has an opportunity to see a bubble because every particle goes down the downcomer. So does that mean it's good for final course? Well, it's actually pretty good for both. You can manipulate the way the downcomer operates. You can change the jet velocity. So if you reduce the jet velocity and operate with low air rates, so all the violence is happening at the top of the downcomer, then if you have successful attachment, it's very quiescent as it leaves. So therefore you can get very high coarse particle recovery. Now, I haven't defined what a coarse particle is in this case. So for us, that's about 300 microns. So we recover 300 micron liberated particles exceptionally well. Beyond that, it really, in coal, we can recover up to 1 millimetre. But once you get into the composite zone, it's just the same as any other device. It's not going to be the first particle to float, so you'll need to put multiple stages to capture those. Because the downcomer is only immersed 900 millimetres below the surface, the actual travel distance for these coarse particles is actually very, very short. So long as it's on a bubble when it exits the downcomer, it has a very high probability of being recovered. And because the froth is so stable, that's another reason that those coarse particles are very, very well recovered. And as I say, in coarse coal feeds, we can manipulate the jet velocity, manipulate the air rate to work out where the flotation happens in the downcomer to actually target the particle size. And of course, it's obviously going to be very good for fines because of the very high turbulence, the high surface area by the small bubbles, and the sheer volume of air that you have in the actual downcomer. Because I'm an absolute supporter of students, I wanted to include, this is a master's that was done by a gentleman at McGill looking at the Jameson Cell. And in this case, he didn't want to listen to just the parameters that I suggested, so he tested pretty much everything you could test. And this chart just shows the bubble size as a function of the water flow rate down the downcomer and the air flow rate. So usually we'd operate at an air-to-pulp ratio in the order of 1. So most of the operations would be operating about in the middle of that curve. But you can see that the blue areas are around about 0.5 millimetre, and the greens, it gets up to 0.7, 0.8. So small bubbles. Once again, a publication from McGill from quite a few years ago, plant bubble size data, just showing we have measured them industrial scale. I'll be interested to see what we get at Mount Isa to be able to compare all the different technologies that they have there. And once again, just because this is something that's vitally important, the machine can generate small bubbles, but without frother to preserve the bubble size, they're just going to grow. So frother is fundamental to the operation of flotation, and particularly so in the Jameson cell, because it drives that extra performance by maintaining those very, very small bubbles. And because the Jameson cell is generally in the cleaner circuit, it's not necessarily common to add frother in the cleaner circuit. People often just rely on residual frother coming from the previous stages, and we would recommend that you always have frother available to make sure you're making the best bubbles. So when you look at the various cell designs, as I said, we've been making these things since the late 80s. We're on to Mark 5 now, so that's the 5th design iteration. And those changes in design have mainly been driven by wanting higher capacity. The early Jameson cells had a downcomer that was about 200 millimetres. Our standard is now 280, and we have a 500 mil downcomer that's mainly used in SXEW applications and in oil sands. So the very big flow rates require the big downcomers. Other design improvements include the way we wash the froth. Obviously the tailings recycle has gone through some iterations because it's so critical. And then the wear parts, we've engineered out any wear problems. So the slurry lens orifice, as opposed to what used to be an orifice plate, now lasts in excess of 5 years. So you don't actually wear out any of the components, which is a huge problem for us because we have no aftermarket parts. But we tried to make it as easy as possible, and all the maintenance can be done by operations and while the cell is actually online. So just to give you an idea, this is a Jameson Cell Mark II, and you can see the slurry distributor at the top feeding into the top of the downcomer, and then the air distributor is the bottom half where the air can get sucked in, and you're controlling the air. So you want it to come out of a distributor so you can have a control valve and a flow meter. This is the Mark IV. As you can see, much simpler design. All of the parts are now quick release couplings, So it's very easy for operations to diagnose any problems. The E cell, which is our rectangular cell, it's just a matter of downcomers. Up to 10 downcomers, we make them rectangular. Beyond that, it's not cost effective, so we make them round. The difference in the recycle, you can see here you have the pump connected to the tailings connected to the feed. So essentially the recycle is internal. Any tailings that is not exiting the dart is going through a recycle slot back to the feed pump. So the hydraulic difference between the tank and the feed pump box drives the tailings to manage a constant feed. Very simple, very effective. Just an example of a 10 downcomer E cell. The B cells, cheaper, round. We go up to 24 downcomers on the round cells. And in these cases, we use external recycle. Example of some coal cells. These are some of the big coal cells at Grosvenor. And this is a base metal cell in Asia. So in this case, you see the box on the floor below. That is what we call our external recycle mechanism. So the tailings go into the box, and then they're split between on-stream or recycle. So once again, a very simple way of controlling the amount of tailings you need to recycle. Doesn't require any operator intervention. And I was just going to show you quickly. This is actually a fairly recent installation at Cadia, and this is their cleaner scalper, their T3 concentrator. And you can just see it's a nice, steady, even flow of froth, nice concentrate. It does pulse because of the downcomer. There is a pulsing action, but nice stable froth, easy concentrate flow, and easy to wash because of the stable froth. So, what are the features that make the Jameson cell suited to being used in a cleaner circuit? So a single cell generally operates between 60 and 90% recovery. So that's not a bank of cells, that's a single cell. And in design, the cell will only be constrained by the amount of tons you can pull off the surface area. Okay, so if you have a very high grade feeding it and you're not getting much upgrade, you've got a very high mass pull, then that could constrain the cell to lower recovery. But generally, at the head of most cleaner circuits, you've got a moderate feed, you're getting a decent upgrade, so you can pull lots of concentrate, and they operate between 60 and 90%. I put equations in there because there are students in the room. But essentially, it's got, because of the small bubble size, it's got high bubble surface area flux, and because of the high froth recovery due to the stable froth, it's got very high kinetics. In addition, this even worse equation off to the right there came from researchers in the US when they were trying to describe the carrying capacity from Jameson cells compared to columns, and they came up with this, which we actually use in design. And once again, fundamentally, it's telling you that the bubble size is a key driver of the carrying capacity, as well as the particle size and the particle density. But air rate, bubble size are the key drivers of high carrying capacity. In addition, because of the physics of it, the hydrodynamics are the same whether you're testing it on a lab scale, or a pilot scale, or a full scale. So we operate with the same jet velocity, all the parameters are the same, so therefore it's directly scalable. So if it happens in a pilot, it happens in the full scale, which is very useful. We don't need any factors, you don't have to multiply it by 2 or 3, because what happens in the pilot happens in the full scale. And in addition, we've found that you can do laboratory flotation tests, 3 stages of dilution cleaning, and we find that scales up very well with the Jameson cell as well. So we have very simple techniques for you to understand what the performance would be in your plant. So this is the cleaner circuit design that we are now recommending, and we've installed at quite a few operations around the world. We call it our preferred cleaner circuit design, really original. The assumption here is that you have done the correct job in achieving the right level of liberation for your cleaner circuit. So your cleaner circuit feed has either arrived with high levels of liberation or you have reground it and now it's ready for separation. That makes the separation very simple. The first cell, the cleaner scalper, is going to take out as much of that liberated stuff in one stage directly to final concentrate, straight away. In some places that operates at moderate recovery, as I say, the 50 to 70. One of the case studies I'll show you operates over 90% recovery in that stage. So essentially if it's liberated, take it out. You don't need to do anything else to it. Clean it up, froth wash it, get the entrained gang out, put it in the con. End of story. The next stage then, I'm showing a conventional cell or banks of conventional cells. It could be a Jameson cell, but most people want to be a little bit conservative, so put a bank of cells in. This cleaner scavenger, the only job it has is to produce a low tail. It has to produce a discard tail. It's the only job it has. So you don't have to worry about con grade because it's going to get upgraded. Just make your low discard tail. Then you send that con off to the recleaner, which will operate at a moderate recovery at whatever upgrade you need to get it into the final con. If it wasn't sufficiently upgrade, send it back, enrich the feed to the cleaner scavenger, provide a higher grade to the recleaner, and then make con of it. Very simple. So now you have 3 pieces of the flow sheet. The cleaner scalper makes the highest recovery at the highest grade. The cleaner scavenger produces a discard tailings, and then the recleaner is the one that the operators sit there and dial and say, well, I need more recovery, I need more grade, I need more recovery. And because the Jameson cell is so fast to respond, the operator is able to do that very, very quickly. So really, once he's set this circuit up, the recleaner is the only cell he has to manipulate to get overall performance. So let's quickly go through a couple of case studies where this flow sheet has been employed. I don't know if any of you have been to Cobar, but it's obviously it's at Cobar in New South Wales. It's a small operation, but an underground mine with very high grade feed. And if you look at this chart, it just shows the average monthly head grade over a couple of years, and you'll see it varies from 3 to 6, and that's a monthly average. So you can imagine the daily average, it can go from 2 to 10. So one of their challenges was always, how do I quickly turn up or turn down to remove the required amount of concentrate? Because one minute it's going to be hardly anything, and the next minute I'm going to be dying, I'm going to be flooded in concentrate. So the purpose of the circuit for Cobar was really to give them the lever of being able to quickly pull out the right amount of concentrate. Their original circuit, which once again was a very old circuit, built, I think it was in the 60s or 70s, it's quite an old circuit, was a fairly standard rougher scavenger con recirculating to the feed. I'm not quite sure why you do that, because you haven't done anything differently to it. But then they operated with a pre-cleaner, so the stuff upgraded pretty easily. They could send some straight to final con, and then a cleaner and a recleaner. Well, guess what? That kind of looks like our preferred cleaner circuit, but with conventional cells. So what we did was we, over time, changed it from their conventional cells that were old and required replacement to Jameson cells. So pretty much the same flow sheet, just all the cells got upgraded. So the roughers got replaced, the scavengers got replaced, the cleaner scavengers got replaced, and then they put in the 2 Jameson cells in the preferred cleaner flow sheet. And you can't see that at all, but you can see on the left there's a 10 downcomer cell, and then on the right there's a small 4 downcomer cell. So the footprint for that cleaner circuit is incredibly small. And what performance does it get? So the cleaner scalper, that first one, taking out nice rich concentrate grade as soon as you can, it operates on the red grade recovery curve. So it operates over 90% recovery at 30% con grade. That's a pretty nice place to operate. So what's left is actually very little. So there's not much left. The recleaner, of course, is going to operate on the grade recovery curve that is going to recover all those slow floating fine particles and all those composites. Because they didn't float up front, you need to float them further down. So as you can see, the grade recovery curve of the recleaner is poorer because you have to float all those other particles. Now you can operate anywhere on that curve you choose to operate, but it is also an indication of your liberation. I went back to Cobar just recently in February, and I did exactly these surveys again, and I found that my cleaner scalper sat exactly on top of the performance from 2014, but my recleaner, the performance was inferior. And it's not because the equipment's inferior, it's because the actual mineralogy has changed and there are more composites. So the performance of that recleaner, it drops off more sharply because there are more composites that need to be recovered. So it's a very good circuit for understanding how well you're doing up front, how well you're liberating, and whether or not there are any changes in your liberation going to cleaner circuit. This is just the same curves showing the selectivity of copper against silica, and as mentioned, the cleaner scalper can obviously reject lots of silica because it's fully liberated. The recleaner, you have to take some of that silica because it's in composite with the chalcopyrite and the cubanite. So how did the circuit perform? The first phase, they just put one cell in, and there was actually a deterioration in performance as they were limited by capacity, and it wasn't until they put the big cell in that they were able to then move to their final position. So the two projects were done over a couple of financial years to spread the capital, and you can see they probably should have done it the other way around. Anyway, so the actual improvement, the concentrate grade from the period immediately preceding it went up by over 1.5%, and the recovery also went up by 0.5%. They've chosen more recently to trade off grade and recovery because you'll see there are some red points that are dropping quite low on grade. They're getting a bit more complex ore. You can see that in the grade of the recleaner concentrate. So they've chosen to change their con targets and operate at a higher recovery, which is so easy to do with this circuit because they have that one lever that says, where do I want to operate my recleaner and what overall grade do I want to finish up with? And because no flotation presentation is complete without some recovery by size, this is just to show they grind to a P80 of about 100 micron, so you wouldn't expect there to be much over 100 micron, and you can see from the copper distribution there's essentially nothing in those size classes. But everything less than 100 micron, essentially you're getting near complete recovery. Good head grade obviously means they can get good recovery, but the overall circuit recovery, you know, in excess of 97, and the concentrate grade is generally around 27. So that was Cobar, very successful implementation of the cleaner circuit design. Mount Isa is a little bit different. Mount Isa, the flow sheet, I mentioned before that I put some Jameson cells in the early 2000s, and one of them was that little cell up there which cleans the pre-flotation concentrate. The pre-float's removing carbonaceous pyrite and talc before rougher scavenger flotation. They also put in new scavengers in the early 2000s, so they had plenty of rougher scavenger capacity. But they were very constrained in the cleaners because the cleaners were still the old 1970 cells, and so they needed replacement. You know, there comes a time in the this equipment is no longer cost effective, and so they elected to do a study on installing Jameson cells to replace the columns, the retreat, and the whole cleaner block. So what they ended up with was this. So they needed 3 Jameson cells to replace the retreat, 3 columns, the cleaner, and the recleaner. And because of our preference to make the final tail with a conventional cell, we kept the cleaner scavengers which had been installed in the early 2000s at the same time as the scavengers. So very simple circuit. The first 2 Jameson cells make final concentrate. The third Jameson cell takes the reground scavenger concentrate and upgrades it. Now, it needs more than one stage of cleaning to upgrade it because of its low starting grade. So it's starting at about 1.5% copper, and we can't make 30% con out of that in one Jameson cell. So it needs multiple stages. So the concentrate from the cleaner scavenger goes to the cleaner, and then the final concentrate grade from the scavenger circuit is made off the cleaner cell. The rougher con, very highly liberation, straight to the cleaner scalper, where it's pulled hard to recover as much of that liberated material directly to final concentrate. I believe JK have just done a very big survey around this circuit, and once again, I'm excited to see the performance of the circuit. So just looking at what it actually means, I've compared for Mount Isa one of their Wemco tank cells, a 100 cubic metre cell, the 3 columns, and one of these 5.4 metre diameter 18 downcomer Jameson cells. Each one of those pieces of equipment, or in the case of the columns, all 3 of them, has a surface area about the same. Okay, so they've got about the same surface area. So if you operated them at the same air rate, you'd produce different bubble sizes because the machines make different bubble sizes. And therefore you'd have different SBs. And then using the carrying capacity formula, you can see that they have significantly different carrying capacities because of that bubble size. And therefore, the tons of concentrate that you can remove are vastly different. Now with the columns, we still suffered the deterioration in bubble size over time. So when we replaced the sparges, the bubbles would improve, and they would wear out over time, and then you'd see that in that the circuit would become overloaded because the columns weren't doing their share of the work. So I've given an average number here. But essentially you can see that the Jameson cell, a single Jameson cell, can recover significantly more tons of concentrate than either of the other technologies. And not only does it recover way more, it does it like that. It does it very quickly. So if you look at the residence time, and I was actually pulled up on this recently saying, well, you're comparing the contact zone in the Jameson cell with the entire column. And I guess the columns that they have there, they're not the more modern ones that pump it round the bottom. They're the old-fashioned ones that just jet air in. So I would argue that most of the column is the contact zone in that case. Maybe I'm wrong, and maybe Kim will pull me aside and have a go at me. But essentially, it happens like that. And in these other big vessels, you have all this space required for flotation. So in the Mount Isa case, they installed 3 Jameson cells, 5.4 metre diameter, 18 downcomers each. It was justified on asset management rather than metallurgy. And initially, the metallurgy was okay, but they did have a few teething problems in learning how to operate what was a very fast responding circuit now. So they didn't have all that time to resolve any issues if they had any. They had to resolve them immediately. So they had to relearn a few things. So what you'll see here is the performance versus their model. So the expected recovery versus a model they have that looks at the mineralogy of the feed and their concentrate grade and the tonnage they're doing, and it gives them an expected performance. So you can see the performance was improving even before we installed the Jameson cells in 2015. So they were doing a better job, or the mineralogy was getting better, one of the two. Then in 2016, after the Jameson cells were installed, the expected recovery was higher, and the difference between the two was not that much. So this was probably the period of time where the operators are learning how to manipulate it. And one of the things of those people who've been to Mount Isa may know is, in Mount Isa the float goes flat very rapidly. So if you add too much collector, you get total bubble collapse. And obviously recovery goes down. And they found that the Jameson cells were way more sensitive to that than the old cleaner banks. So if the roughers went flat, the Jamo used to go flat straight away. And that's probably the cause of the lower recovery. They found and did some studies around the surface chemistry, trying to understand why why the float goes flat. And they used an old operator's trick that I learnt from the operators back in the early 90s, which is, if in doubt, add cyanide. So they added cyanide to the Jamo, and lo and behold, it got better. The bubbles improved, they loosened up, the mass pulls were very high. I'll leave it to you researchers to tell me why that's the case. Just don't tell them to turn it off, because it works a treat. So essentially, once they'd resolved those chemistry issues, then moving forward, the performance has improved, and hopefully the results of your survey will demonstrate a significant improvement of the circuit. So this new circuit reduced the cell volume by 57%. So you've got a lot less equipment, a lot smaller equipment. There was a 71% reduction in froth surface area. There was a 27% reduction in froth lip length, and a 70% reduction in residence time. Yet the performance is the same. So that should tell you, for cleaner circuit design, you don't need all those things. You just need the right bubbles to get the job done. Once again, because it wouldn't be right to not show you the recovery by size for that circuit, I chose two periods that are about the same concentrate grade, both about 26, and you can see, you know, no error bars because I didn't have enough information, but essentially it's the same performance. You'd be hard pressed to say those two lines were different from each other. So there's no issues, and I like to think that now that they've resolved the surface chemistry issues that were still prevalent in March, that those fines recovery should be improved. So that's what I'm hoping to get out of the JK survey that was done at Mount Isa. So this, for those of you who didn't go to Mount Isa, these are the 3 cells. So essentially those 3 cells and 2 100 cubic metre tank cells are the entire cleaner circuit, removing it's more than 500,000 tonnes of concentrate a year. So, you know, it's a very small cleaner circuit, very cost effective. And that's the froth being removed from the 3 cells. So when it comes to cleaner circuit design, significant reductions in plant footprint can be achieved if you use Jameson cells. They can be achieved with any technology if you use small bubbles. If you use small bubbles, you can get high carrying capacity, you can get high tons of concentrate per square metre of area. So that's really what you're after. But the difference with the Jameson cell is you don't have a residence time factor. So you don't then have to say, well, I need 7 or 8 of them in series to get my number of stirred tanks, or to get the 30 minutes, which is my lab times 3. It's just a matter of how much concentrate do you need to remove, and therefore how many cells do you need to remove that amount of concentrate. So residence time's only one parameter. And froth carry rates for the Jameson cell are way more important. Froth carry rates, lip loadings, way more important for Jameson cells. If you have a higher volume, you add more downcomers. If you have more mass to remove, you need to add more surface area. The fact that they have very intensive bubble particle contact and the spore bubbles means it's very fast flotation, and that's why we can get these high carrying capacities. So at Mount Isa, we consistently get over 5.5 tonnes per hour per square metre off that, particularly off that first Jameson cell. And in Cobar, when I was last there, I measured 7 tonnes per hour per square metre. So it's a function of the particle size, you know, what the mineralogy is like, but you can recover lots and lots of tonnes, and most engineering houses would not use those sorts of numbers. So the cleaning circuits, when used in conjunction with the existing capacity, can be very effective at achieving high grades. Because of froth washing, you're not putting any accidentally recovered material into your con. So you're getting the best possible concentrate grade because you've removed all those accidental particles. It's a 30-year-old technology, but it can still be highly innovative even though it's old. And I'm hoping that the base metal adoption curve is now on the up and up, and people can realise that the technology, although brought to industry before it was ready, is certainly ready now. And one of the reasons I know that it works well is the first time we installed this circuit was in North Parks in 1994. The original circuit I don't believe was set up this way, but the resultant circuit, which has 4 Mark II Jameson cells, is now arranged with the big cells as cleaner scalpers and the small cells as recleaners. So it's been proven to be an effective flow sheet for quite a long time. Thanks for listening.